My name is Stephanie V. Shea, and today I'm presenting on HIV antiretroviral resistance. Thank you for joining me, and I'll try to keep you entertained during this short presentation. What is HIV? We're going to start with a little epidemiological background on HIV, and then move on to the virology of HIV, focusing on its genetic structure and classification. It is estimated that between 65 and 113 million people have been infected with HIV since the start of the pandemic around 1984. An estimated 32.9 to 51.3 million people have died from HIV and AIDS. It's believed that approximately 39 million people are living with HIV worldwide as of 2022. HIV is enveloped and has a single-stranded RNA genome. As it codes for reverse transcriptase, it belongs to Group 6 of the Baltimore classification system. It is spherical in shape and may be pleomorphic, which means that their shape can vary slightly. And they are about 1,000 to 1,500 angstroms in diameter. A brief overview on the replication of the HIV viral particle. Infection begins when the viral surface protein, GP120, binds to the CD4 receptor, most often found on the surface of T helper cells. Viral entry is further mediated by a secondary receptor, either CCR5 or CXCR4, depending on the strain of the virus. Binding to the secondary receptor prompts an additional conformational change in the GP41 subunit, which then triggers the fusion of the viral envelope with the cellular membrane, allowing the viral capsid to enter the host cytoplasm. Once inside the cell, reverse transcriptase, a viral enzyme, and the viral RNA are released from the capsid. Reverse transcriptase converts the single-stranded RNA into double-stranded DNA. The reverse transcription process is particularly error-prone, leading to a high mutation rate, further compounding HIV antiretroviral resistance. The newly formed viral DNA is next trafficked to the nucleus, where it is integrated to the host DNA by the viral enzyme integrase. This step is absolutely necessary in order for the HIV to hijack the host replication machinery. Transcription and translation are next. Now part of the host genome, the integrated viral DNA instructs the host cell to start mass-producing viral RNA. Some of this newly synthesized viral RNA is used as genomic RNA, meaning it was produced in order to build new virions, whereas the rest of the viral RNA will be used to direct the synthesis of new viral proteins. The proteins in RNA will begin to assemble at the cell's plasma membrane. Initially, the GAG protein will form the matrix of the viral particle, then the GAG pol polyprotein will be cleaved by the viral enzyme protease. This sectioning splits the larger molecules into the functioning components, including reverse transcriptase, integrase, and protease. The virions exit the cell by budding. They become enveloped in a portion of the host cell membrane that incorporates viral glycoproteins like GP120 and GP41. Maturation occurs outside of the cell and is accomplished once the viral protease cleaves the polyproteins one last time in order to make new infectious particles. And we'll see why all of this is important in terms of antiretroviral resistance in the next few slides. We'll succeed to a degree. This is the chronic phase, also known as clinical latency. This is also the time that the virus integrates with the host genome and hides out in resting CD4 plus T cells. The immune system attempts to respond to the infection. It mounts a targeted attack against the foreign invaders with HIV-specific antibodies and cytotoxic T lymphocytes. But the virus evolves too quickly due to its high rate of mutation. The hallmark of HIV is the progressive depletion of CD4 plus T cells, and this renders the host susceptible to opportunistic cancers and infections. A characteristic fades. This development usually takes between 8 and 10 years without treatment. The criteria for AIDS The criteria for AIDS is a T cell count less than 200 cells per microliter, in addition to some sort of opportunistic infection. What is HIV antiretroviral resistance and how is it caused? In simple terms, HIV resistance involves a series of mutations that change the genetic structure of the virion. These mutations change the physical layout and chemical properties of the proteins encoded by the viral genome. This is of particular concern when these evolving proteins were once the targets of antiretroviral drugs. As a result of these mutations, the altered viral enzymes may no longer bind effectively to the medication designed to inhibit their replication. In essence, HIV resistance provides an escape path for viral particles to continue replicating even in the presence of antiretroviral drugs, presenting a significant challenge for the effective treatment management. The big picture question is, what are we doing to combat HIV antiretroviral resistance? HAART used to be the go-to treatment for HIV, which is a highly active antiretroviral therapy and includes a combination of 3 or more antiretroviral drugs, usually of 2 or more classes. This may have proven quite toxic to the host, and due to advancements in antiretroviral drugs, ART was implemented, which now can consist of a single, more tolerable drug. Emphasizing combination therapy, scientists are able to target the virions from multiple angles, reducing the risk of resistance. Today, we pin our hopes on the development and innovation of new antiretroviral pharmaceuticals. On this slide, we'll be focusing on 2 new innovative medications aimed at combating HIV resistance. Lenacapavir is the first of its kind to employ a long-acting capsid inhibitor. It's administered once every 6 months via subcutaneous injection, and resistance is rare due to specific mutations in the capsid inhibitor portion of the GAG protein. Additionally, spirobeta-lactams show impressive activity against both HIV-1 and HIV-2, making them promising candidates for clinical trials in the future. The next step should be focusing on initiating clinical trials to assess the effectiveness and safety of promising newly synthesized compounds like spirobeta-lactams and lenacapavir, especially for those individuals infected with HIV-2. Research should be expanded to elucidate the mechanisms underlying these novel compounds and their resistance patterns. Advancements in new antiretroviral drug development will be essential for the future in combating new pathways of resistance. Exploring combination therapies that combine these novel compounds with existing antiretrovirals may prove promising in combating both viral load and resistance. Thank you so much for taking the time to listen to my presentation of HIV antiretroviral resistance. And here are my sources.